hopefully I won't take a lot of your time today. I would like to introduce myself. I'm Mohammed Darwish. I'm an adjunct faculty at the American University in Cairo, and I'm also a part-timer at the German University in Cairo. Today I'll be talking about the design of funicular arch wooden falsework. So, first of all, we need to understand the current situation of most of formwork systems and falsework systems used in Egypt and in similar countries. So typically, falsework systems are what we are called in Arabic shadda. They are typically made of wood, as you can see over there. And these wooden members, they are not that nice in terms of two things. First, they block the space here. So you don't have a lot of availability to have a lot of construction activities down here. Second, they are a lot in terms of a lot of wood. More wood means more cutting trees, something bad to the environment. So actually, this system is composed of mainly secondary beams, called joists, main beams called stringers, and shores, represented here by these black points. So whether the shores are wooden or not, they are typically larger number, so they have more costs and they allow less space. And this takes us to another point, that we could replace that system, that bad, a lot of amount of material consumed, with another alternative. So this is what we call a funicular arch. A funicular arch is actually it's a concept that has been used for a lot of years. Okay. However, in other applications other than this application. So the current study proposes a funicular arch wooden truss that minimizes the forces within its members and hence minimizes the midspan deflection and the need for cross-sectional area. This newly proposed temporary structure is replacing the use of 4 spans of stringers and 5 shores supporting them by one single truss. Within the study, the variation of the forces within each type of members is studied with changing the span. Also, this variation is compared to the variation in the straining actions of typical stringer shore designs upon changing the spans. Also, a weight comparison was very interesting to be performed. So, first, to understand the concept of this funicular arch, an arch is considered funicular, which means only having compression within its members if it is hinged at both sides and it has an intermediate hinge here at the middle. So, and it must obey this equation in terms of curvature. Okay? So, what's very unique about a funicular arch truss is that you don't have any forces in the diagonals or the upper chords. So you have a lot of zero members, which is saving a lot. The upper chords in our case were considered as mainly 2 pieces, one covering 4 bays and the other covering the other 4 bays. So this A is actually the distance of 1 bay, and so the span is 8 times A. So that minimizes the bending moment within this member. The axial forces for each of the 6 internal verticals were very simple. It's equal to W times A. While the axial forces in the lower chords were proven using the method of joints to be all obeying this relationship, which is the axial force is equal to W times the length of the member times the span of the truss divided by the height. So first, I have to validate my model, or actually my closed form solution, by comparing the different forces that you could see here produced from SAP, okay, but to whatever we have from the closed form solution. So this was done for a 3.2 by 3.2 meter truss, and a distributed load of 22.5 kilonewton per meter was applied. The diagonal and upper horizontal members had negligible axial forces, which is fair enough because they are supposed to be zero members. The axial forces within the other members were only 0.8% different than whatever you have from that closed form solution. So now our closed form solution is valid. We know that we are valid, so we could start the parametric study. So 8 different trusses were analyzed and designed. the studied spans range from 3.2 meters up to 6 meters, which was surprising for me, because we could get good values from the span. All the trusses had a height of 3.2 meters. The variation of the frame actions within each member was studied. The mid-span deflection of the truss was also studied. The members were designed to satisfy the safety and serviceability design criteria. And when talking about safety and serviceability design criteria, we are talking about two different things actually. Safety is actually more related to maintaining a certain stress which is below the maximum allowable stress. Okay? However, serviceability is maintaining a minimum deflection, minimizing the deflection to be less than the maximum allowable deflection. Our design is satisfying both. The more interesting part, or actually what I believe is the fruit of all this thing, is that the weight of each truss was compared to that of the conventional alternative system involving 4 spans of stringers with 5 shores supporting them. So now, I'm comparing this innovative solution to the very conventional formwork system. So looking at structural performance here, when comparing the mid-span deflections that were attained, they were always significantly less than the maximum allowable deflection, which could tell us that this thing, in terms of design, it is a very sound design from terms of safety and serviceability. Now, the fruits of this study. The real fruit of this study is a real significant reduction in the amount of wood that you would use in such a thing. Here, the blue ones are the regular stringer shore systems. However, the light blue ones are what? These are our design. Okay? So you could see a significant reduction in weight for all of the cases, which ranged from maybe 35% up to 56% in some cases. So this is a reduction not only in the cost, it's a reduction in everything. You're reducing the amount of wood. You are reducing the time consumed in assembling such a thing. And you are also reducing the time wasted in the passage beneath, because now you have a very easy construction site that you could move in. So this is actually perfect for, I believe, also fast-track projects. And if you know more about construction, one of the most time-consuming activities is the formwork activities. And actually, one of the most non-environmental friendly activities is the formwork, because you're actually cutting trees. So now you cut less trees, okay? So this is the main conclusion here, that the newly proposed system could have an average savings of 46% in the material costs of the falsework. Not only the material costs. By the way, the labor cost was not included in this study yet. I'm saying yet, because we will be. Sorry. So also we have a set of recommendations, because I know this thing is still on paper. It's still on paper, it's still on the computer. We need to have a full-scale model of this proposed design, in order to be sure that everything is done properly. The details of the connections need to be really studied thoroughly, because here there is an assumption that it is a perfect truss and that the connections are a pin-pin connection, 100% non-transferring moments. However, in reality, there is nothing called a pin-pin connection. You always have what we call partial fixation. The response of the proposed design under wind loads needs to be studied, but I don't think this is available in Egypt. You could go to my place that I like. I got my PhD from Western Ontario in Canada. So over there they have a wind tunnel. If we have enough money, we could do it. Okay? Then a cost analysis needs to be performed in order to compare the cost effectiveness of the proposed design to that of the patented systems or readily available in the market, because needless to say, we all know about patented systems. We all know about steel falsework that's available by a lot of companies like Perry, Docker, a lot of companies have that stuff. So this thing, it needs to be done for sure. Okay? Finally, I would like to thank you all, and I challenged the moderator today that I will be